Megan looks right.
Oh my god.
All right, let's take a look at page 186. Yesterday we were looking at what it meant. We were looking at yesterday what it meant for a function to be differentiable. Okay, meaning that the derivative exists, and there were three kind of special points on a graph that we could look for to see where a derivative did not exist. Can we describe those shapes or those characteristics from yesterday? Go ahead, Austin. An endpoint, definitely. Sure. Yeah.
A sharp point.
Sharp point, aka. Do you remember the other word for it? Yeah? Cusp. Okay, so sometimes you might see the word cusp. That just means sharp point. All right, endpoint, sharp point, vertical tangent, vertical slope. Good. Okay, so graphically we were looking for those characteristics yesterday. We're going to try to determine what the characteristic is like analytically, okay, by hand, just using an equation. So somehow we're going to analyze, in this case, the g of x piecewise function, and we're going to check to see if it's continuous. It's kind of a review question from earlier this year, but then we'll check to see if it's differentiable. Okay, does the derivative exist at that spot? So we'll deal with this as a continuation from yesterday in a little bit. Let's check out continuity. What was our holy trinity for continuity? Yeah?
Absolute limit and value, and then they match.
Okay, so absolute limit from the left and the right, value meaning point, and then they have to match. So it doesn't matter if you check the point first or the limit first. Okay, the order doesn't really matter, but you got to check both of them just to see if they match. Maybe we'll try the point first. So we're checking the continuity at 3, and notice how that's kind of the interesting location on our graph, because 3 is where the first equation ends and the next one begins. So we're basically trying to make sure that this left and the right side graph meet up. Okay, are they the same? Do they meet at a closed circle? Which equation can we plug in 3 to check the point? The top one, because we have that equal bar. So the square root of 4 would be 2. All right, so our point exists. Let's go ahead and check out the limit. So we'll have to do the left of 3, but also the right of 3. So the left side would be the square root equation, and the right side would be the line. What do we try first for a limit? Substitution. All right, plug it in. So square root of 4 equals 2. 5 minus 3 equals 2. Are we continuous? Yes. Notice how the point matches the overall limit. So for 3, they match. We'll say continuous because g of 3, the point, equaled the limit as we approach 3. So we know the left and the right side are connected, okay, where one ends, the other one starts, so they're connected perfectly. But when we start to analyze if we're differentiable, we want to see, are we connected smoothly, okay? Because if the left side and the right side are connected smoothly, notice how we would have a slope there, okay, and the slope is the same for both of them. If we're not connected smoothly, that's what's going to create that sharp point that we were analyzing yesterday. So in order to check differentiability, it's very similar to this limit process, but instead of checking the left and the right equation, we got to check the left and the right slope. Okay, are they connected smoothly? Okay, so we'll say check left and right slope, aka derivative. Okay. So the left side would be this square root equation. So how do you want to find the derivative of the square root. Can we think of a shortcut we can use? Chain. Okay, so maybe you want to rewrite it as x plus 1 to the 1/2. So our chain rule, we'll bring down the 1/2, keep the inside. New power would be -1/2. Finish the chain rule by multiplying by the derivative of the inside, which would be 1. So if we clean this up, bless you, we have a negative power, so I'll move that to the bottom. And then the 2 from the 1/2 can stay on the bottom, and we'll have the 1 left up top. So this is our derivative on the left-hand side. Let's evaluate it at 3, because we want to see what is the slope at that spot where that graph kind of ends, but we know the next graph is going to pick up there. So if we plug in 3, what will we get? 1/4. Okay, so this is the slope from the left-hand side. Left slope. We got to now check the right-hand side to see if it has the same slope, meaning that they're smoothly connected. So the right equation would be the 5 minus x, and if we do our derivative shortcuts, the derivative of 5 is 0 or nothing, and then we have to subtract the derivative of x, which would be -1. All right, so there's our right slope. Are they smoothly connected? No. So if you think about it, like on the left-hand side, your slope is 1/4, so maybe something really shallow like that. But then on the right-hand side, your slope is -1. Now I know it's backwards for you, so it'd probably look like that, right? Is that right? Okay. Notice how it's creating that sharp point, okay, where my fingertips are touching. So they're not smoothly connected. You have that drastic change in slope, aka direction. So we can say that we are not differentiable at x equals 3 because the left slope does not match the right slope. So in terms of a graph, if we actually had a picture, we can say there is a sharp point or a cusp at x equals 3. We know we're continuous at 3, so the left and the right side are meeting up, but they're just not meeting up smoothly. And that's not creating a derivative for us, okay, a slope at one point. Do we think that's a simple concept? Check the left and the right hand slope. We're going to see if they match. Okay, very similar to our definition of continuity. All right, let's check out the next one. For which values of k and m will the function below be both continuous, so the left and the right side meet at a point, and differentiable? So not only are they meeting, but they're meeting smoothly. Okay, smoothly connected. So we got to check two things here. Let's check continuity, and then we'll check differentiability. So if we think about continuity in terms of our equation here, we know we're going to have to plug in 3 somewhere. And the point would exist because we do have a bar on one of those 3's. What we're really interested in, though, since we have these other variables, the k and the m, to consider, we really want the limits to match as well. So we want the left-handed side to match or equal the right-handed side. We can simply write k squared of x plus 1 equals mx plus 2. All right, we want the left and the right to match. Since we're specifically checking the spot of 3, we can go ahead and kind of get rid of the x variable by plugging in 3, one less variable for us to worry about. So if we plug in 3 for the first x, we'll end up with 2k and then 3m plus 2. But in order for us to solve for k and m, we're going to have another equation to kind of set up a system here, because right now we just have one equation with two variables. So that other equation is going to come in from this differentiable part. So for continuity, we want the left and the right sides to match, but for differentiability, we want the left and the right slopes to match, okay, aka derivative. So if we were to think about finding the derivative of our first function, remember, k and m are going to be numbers. Okay, they're not variables anymore. Maybe we can do a chain rule on this first function here. So if you rewrote it as a power of a half, that might help. So if k is a number, we'd have to take k times the 1/2. That's like bringing down the power. We'll keep the inside. Our new power would be -1/2. And then times the derivative of the inside, but that would just be 1. So there's our left-handed slope. What about the slope on the right-hand side? If m is a number, it's just going to be m. All right, maybe we can clean up the left-hand side. The x plus 1 can move to the bottom, and then the 2 would be there as well. So just like the last example, we can get rid of the x variable because we know we're checking a particular point. So if we plug in 3 for that x, we'll have k over 4 equals m. So where do you guys want to go from there? Right now we have two equations, two variables. We should be able to use a system to help us out. Do we want to do substitution, elimination? Do we have a preference? Is one kind of set up more appropriately for us right now than the other one? Which one? Substitution. Notice how m is already solved by itself. So we can take the k over 4 and plug it in for that m. And then we just have some old school solving from there. So let's see. I'll write this as 3/4 k. So if we subtract 3/4 to the other side, we'll have 2 minus 3/4. So that would be 5/4. Good. 1 1/4. So that'd be 5/4 as a fraction. Okay. And then solving for k, we can multiply the 4 over, but then divide the 5. So we'll get 8/5. So now that we know what k is, you can plug it back into either equation to help you solve for m. Maybe the second one would be a little bit easier. So we'd have 8/5 divided by 4. Instead of dividing by 4, you can multiply by the reciprocal, so that would be 8 over 20. But 4 can go into both of those if we simplify it, so 2 over 5. There's our m value. So I know they're not whole numbers like we would like them to be, but nonetheless, these are the values that k and m must be in order for the left and the right to match, okay, be continuous, but also to be connected smoothly, meaning that the derivative or the slope would exist at 3. Okay, so we're checking two things here. Are they connected? And then are they connected smoothly? Okay, that's the derivative or differentiable part. Do you guys think you can try the next one?
Sure.
Yeah, for what values of a and b will the function be differentiable? What did we say the word differentiable implies? Same slope, smoothly connected. If I say a graph is differentiable, what does it also mean? Also imply, also signify? It's continuous, okay? So by stating this word, they're basically asking you for which values of a and b will the function below be continuous and differentiable. So by using this word, it's also implying continuity. So just like the previous one, we're going to have to check for continuity and if it's differentiable. Okay, are they connected, and are they connected smoothly?
Yeah. What do you have a decimal.
Not really. So this would be 11 over 2. 11 over 4. So this is 11 over 2 over 2. So that'd be 11.
That's what it is. Cause I can't do it. Because you can't have, it's unprofitable.
All right, so I'm walking around and this looks really good. I'm curious as to which method we use to help us with the system.
Elimination.
Elimination? Yeah? Okay, kind of sets itself up well for that. If you tried to do substitution though, I would suggest using the continuity equation, because when you solve for a variable, you'll end up with nice whole numbers, because notice how they're all even. So if you divide by 2 for A, it would work out nice. But we can always do the elimination part. All right, so I'm going to, I know you're used to adding the equations together, but in order to cancel out the 2 A's, we can always subtract them as well. Hi. Tyler, can you just leave it on the desk right there? Thanks. Is that your lunch? All right, so if we subtract the equations, depending on how you set them up, as long as they're stacked correctly, that's fine. Solving for B, we'll get 1/4, okay? And then plugging that back into either equation, it doesn't matter. Let's see, 2A plus 3 over 2 plus 4, 2A plus 11 over 2, negative 11/4. Okay, how do we do?
Good.
Perfect?
You couldn't plug it into the derivative equation, could you?
Yeah, you could plug it in that one.
Oh, sweet.
It would work out either way. Doesn't matter. All right. So we're going to stop there for today. I don't feel comfortable starting the next section because it's a different topic. But in the remaining time, you could definitely use this for homework questions or asking any general questions. Okay? Just a reminder, quiz is coming up next week on the 6th. And then unit test the following week, the 11th and 12th.
Can we actually